have given you the definition of the vertex cover problem. I showed you the input, I showed you the output. That defines the problem. Now we are going to see in more depth a mathematical formulation for the problem as an integer program. An integer program has three parts to it: variables, constraints, and an objective. Let us start with the variables for modeling the vertex cover problem. A vertex cover is a subset of all the vertices in the graph. How do we model, how do we represent a vertex cover? Well, how do we represent a subset of vertices of the graph? For each vertex of the graph, we need to know whether or not the vertex is in the subset. Two possibilities. So let us define one variable for each vertex of the graph. Vertex A gives us variable x sub a that takes on two possible values, 0 or 1, depending on whether vertex A is in the subset. xa equals 1 means vertex A is in the cover. xa equals 0 means vertex A is not in the cover. We do this for every vertex in the graph. N vertices, this gives us n variables. Two possibilities for each variable, this gives us 2 to the n possible assignments of our variables. So that's our variable set. Next, the constraints. A vertex cover must cover every edge in the graph. How do we capture that mathematically with an algebraic expression? Let us consider one of these edges, say edge AB. We have two variables, x sub a, x sub b. Each of them takes on two possible values, so we have four possibilities. 0, 0, 1, 0, 0, 1, 1, 1. In the first case, 0, 0, neither A nor B are in the cover, and so the edge is not covered. In the other three cases, the edge is covered. Now, what we need is an idea. The idea is, let us compute the sum x sub a plus x sub b. And observe, in these four possibilities, what do we have? 0 plus 0 equals 0. In French, we say 0 plus 0 égale la tête à Toto. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 2. So the four possibilities for the sum are 0, 1, 1, 2. And we want to express the fact that the bottom three are a cover of the edge. The first one is not valid. Very simple. X sub a plus x sub b is greater than or equal to 1. This expresses the fact that our vertices cover the edge AB. Going from one edge to an entire graph, we write one constraint for each graph edge. And so we have a whole set of constraints, of linear inequalities, that together express the fact that the subset of the vertices is a vertex cover. Finally, we want the vertex cover that has minimum weight. How do we write this? We write this using an objective. The objective is to minimize x sub a times 1, because if A is in the cover, since A has weight 1, it contributes 1 to the cost, plus x sub b times 4. If B is in the cover, it contributes 4 to the cost, plus 4xc plus 2xd plus 9xe plus 4xf plus 3xg. That's it. That's our objective. What is the relation? To recap, if you look at the green vertices A, C, D, F, G, observing the graph, you can see that every edge is covered. It's a vertex cover. Summing their weights, you can see that the value is 14. Corresponding to that, there's an assignment of the variables xa xc, xd, xf, xg are all equal to 1, and the other variables are equal to 0. You can verify that all the inequalities are satisfied because all edges are covered, and that the value of the objective is 14. In general, for a general graph, you have one variable per vertex. You have the constraint that for every vertex in your graph, every vertex u, variable xu must be equal to 0 or equal to 1. And for every edge of the graph, you have the constraint that if the edge is uv, xu plus xv has to be greater than or equal to 1. Given these constraints, your objective is to minimize the sum over every vertex u in the graph of w sub u times xu. This is an integer program for vertex cover. There's a one-to-one correspondence between vertex covers and assignments of the variables that satisfy all the constraints. And the value of the vertex cover is the objective value of the corresponding assignment. Thus, I have given you an integer program that is a formulation for the vertex cover problem. Now, we are going to see a linear programming relaxation for vertex cover.